today's topic, a very important and very classic probability question, which is the birthday problem. What we're going to examine is the probability, and I'm going to start off with a scenario here where I think we'll just start very basic and look at months. And the question that we have here is the following. If we have a group of 6 people, so a group of 6, what is the probability? So find the probability that at least 2 have the same birth month. At least 2 people have the same birth month. Now what we mean by that is, of course, you have 6 people in a group, and we're looking at probability that maybe 2 of them were born in September, or more. Maybe 3 of them were born in September, or maybe 2 of them were born in March, or maybe 4 of them were born in April, and so on. So that's what we're after here. Okay? Find the probability that at least 2 people or more have the same birth month. Now the way we're going to do this, we're going to start by looking at a tree diagram. So this is not, this isn't the birthday problem yet. This is the birth month problem. So we're starting off kind of sort of carefully and gingerly and getting our feet wet, and then we'll build up to the big one. Okay. So I'm going to start off with a tree diagram here, and it looks something like this. We take person number 1, and they're going to be born in some kind of a month. Okay? Now, if we go to person number 2, 2 things can happen. Either they're born in the same month as person number 1, or they're born in a different month. So I'm going to call this different and same. Okay? So what we're really doing here is person number 1, and this is like person number 2 happening there. And then we mosey on to person number 3, and whichever branch we follow, okay, person number 3 will be different or same. And down here, different or same. Okay. And then, of course, we go on to person number 4. So we'll have branches going on here. Now, I'm running out of space, but I also don't need to continue, because what I'm going to do is see if I can find some kind of a pattern of probabilities with these first 3 and kind of make my conclusion here. So here's what we're going to do. We're going to look at probabilities and say, well, what is the probability of person 2 here having the same birth month? Well, there are 12 months to choose from, one of which belongs to the person number 1's birthday. So there are 12 months to choose from, and having exactly the same would be a 1 out of 12 probability. So that means that there are 11 out of 12 that are going to be different. Okay? Then we mosey on to person number 3. And this time, because there are 2 previous months to choose from, we follow, for example, this branch here. This person might be born in something like, let's use September. And then this is different, so we'll say October. Now, in order to be the same, we have 2 months. Remember, it only has to be the same as one of these. So it could be September or October. So to be the same, we have 2 months out of 12 as our probability. And to be different, we have the remaining 10 months out of 12. Okay? Now, I could work out probabilities down here, but it's not really necessary. And I'll show you why here in a moment. If we look at this tree diagram, which obviously isn't finished and quite a bit bigger, in order to answer our question of at least 2 people having the same birth month, basically that would be almost every branch combination that we have. For example, we went this route here and went person 1, and then person 2 is different, and then let's say we went to person 3 is the same. Bingo, we're there. Okay, so everything that follows after this doesn't really matter. All of these branches here are going to be considered successful and part of our probability because of the match between this one and presumably one of these here. Okay, same thing here. If we go person 1 and then person 2 is the same, then all these branches here are going to be considered successes because we're going to have 2 the same, maybe 3, who knows, doesn't really matter. There is one branch, however, that isn't part of our solution of probabilities, and only one branch, and that is every person is born in a different month. So what we want to do is say, instead of working out all these different branches and their probabilities, and then adding up those probabilities and saying, aha, that's our answer, we're going to use something that's called the complement. So instead of saying we're going to work out these probabilities, we're going to say, let's do this. We know that all probabilities add up to 1. 1 representing 100%. Okay? Every probability in this problem has got to total, if we add them all up, 100%, or 1. We're going to take away the very one branch that we don't include in our solution, and that is that everybody is born in a different month. So this is what we're going to do. We're going to take 1 and then subtract only one branch to calculate, and of course our answer is then that will be the probability of at least 2 the same. So that's our strategy. It's a lot easier to do it this way than to try to work out all these other different branches, and there's quite a few branches. Way too messy. So here's how we do it. Let's find out the probability of different. Well, the last time we looked at probability, we noticed that it's very easy to do probabilities along a branch. You simply multiply them together. So all we have to do is this. We're going to go 1 minus, and so the first probability we have is 11/12 times that by 10/12. And of course you can see the pattern that's happening here. The next number would be 9/12 and 8/12. And now the question is, how far do we go? Well, we had 6 people in this group. If we look at this, when we got to the 11/12, this represents the second person. So this would be the third person, fourth person, fifth. So we need to do one more. And that gives us the correct calculation. That these representing the probabilities of the remaining 5 people after person 1, giving us a grand total of 6. Now this is small enough calculations we could easily do this on our calculator. So let me just make a little bit of room here and show you one way we could do it. And that is, we can just directly work this out and say, okay, we could go 1 minus, and what do we have here? 11 times 10 times 9 times 8 times 7, and then divide that all by 12 to the 1, 2, 3, 4, 5, and we'd work out our answer. That's a good way to do it. There's just one little problem with that method. What if there was more than 6 people? And what if there was 40 people in the room? Well, all of a sudden, you're working out whatever these numbers are. The point being is there was 5 multiplications in a group of 6. If there was a group of 40, we'd have 39 multiplications. And that's starting to get really messy. So we're going to try and find a better way to do it. And I'm going to use a little trick here. I'm just going to back up and say, well, this is good, but there's an easier way built into all of our calculators. But what it's going to involve is I'm going to do an extra little fraction here. Okay? I'm going to throw in 12 twelfths. Now I can do that because 12 twelfths is the number 1. And throwing 1 times all of this actually doesn't change it. But this has one little advantage. Okay? First of all, how many fractions do I have? Well, I have 6 fractions. Same as the number of people in our group. And that makes it a lot easier to remember what to do. So instead of having 12 to the 5th and sort of having to try to remember, oh, it's not exactly the same as the number of people in the room, it's easier if I did this and said, well, let's make that 12 to the 6th. So that's the same as the number of people in the room. And the next thing I'm going to do is, well, how can I work out what I have on the top, which would now look like this? Of course, I've thrown in that extra 12. So how do I deal with this 12 times 11 times 10 times 9 times 8 times 7? Well, if you think about it, that can be worked out using something that you saw in a previous lesson, and that is to use a permutation function that's built into your calculator. In other words, let me convince you of this. I don't think we need this down here anymore, so just convince you of this. If I said, what is 12 pick 6, if I went to what that actually means, that means that we would have 12 factorial divided by 12 minus 6 factorial. And if we expand that out and have a look what that actually is, 12 factorial is 12 times 11 times 10 times 9 times 8. Whoops, running out of room here. I'll keep going, I guess, down. No, that's going to be, I'll just start over here. Equals 12 times 11 times 10 times 9 times 8 times 7 times, I'm going to put 6 factorial instead of writing the rest. And of course on the bottom, 12 minus 6 is 6 factorial. So we'll get rid of this so it doesn't look like it's confusing us, and we've just written it here. Now of course the 6 factorial cancels with that 6 factorial, and what do you really have here? You have 12 times everything down to and including 7, which is exactly what we have up here. So a nice compact way of writing this with a function built in your calculator is to say 12 pick 6. Now that's a lot easier to do on your calculator and has a real distinct advantage here. You'll notice that in this particular formula, there were 12 months to choose from. Okay, we have a probability that's always built over 12. If you're talking about one person and then the second person, it was, well, they have a 1 in 12 probability of having the same birthday, or 11 over 12. Now, so 12 has to do with how many things there are to choose from. And the 6 over here is how many people are in the group. So what we have here, oh, and incidentally, I guess I'll give you the answer here. I worked that one out ahead of time, and what we get here is 0.7772, or, if you like, approximately 78%. So that's very, very likely, in fact, that you're going to have at least 2 people with the same birth month. Now let me expand on this particular formula here, because that makes it really easy when we go to the classic birthday problem. The formula, in essence, looks like this. We simply go 1 minus, and if we're talking, let's see, if they have the same, well, let's use the birthday problem. If they have the same birthday, we have to ask, well, first of all, what would be the bottom number if we were to work out these probabilities along a tree diagram? Well, we would be talking to the probability of being the same would be, for the second person, 1 out of 365, and to be different would be 364 out of 365. So instead of 12, what we want is 365. And so up here I would have 365 and pick. Now, in here we had 6 people in the group, And we're just going to pick a number here. The one that I worked out ahead of time actually was, what if there were 38 people in the room? And so I would raise that to 38. So I'm kind of extrapolating from what we did here for months, and now I've made this the answer really to the classic birthday problem. And what we have here is, in a group of 38 people, the probability that at least 2 people share the same birthday. I'm not talking about the same year here. We're just talking about the same birthday. Like if you were born September 16th, somebody else might be born September 16th. So they share the same birthday. So that's what we're talking about. We've set that up here. The group of 38 people. We're talking about birthday. So there's 365 days that we're working with here. And if we go ahead and work this out, it's actually quite surprising that it's so likely. I worked this out and got 0.864. Or about 86.5%. So it's very, very likely in a group of 38 people that at least two, are going to share the same birthday. So this is what we call the classic birthday problem. So you can have a lot of fun with it. You might find, depending upon your calculator, I know I've got a bit of a dated calculator, and it has perhaps not the memory capacity of some of the newer ones. So if you have an older calculator, for me, I can't work out once I get to 40 people. It gives me what's called an overflow error. What that means is that these numbers are just so big, like 365 raised to the 40th, it's simply too big for the calculator to handle. So it has what they call an overflow problem. So be aware that that can happen to your calculator. Hopefully you got a new one and you won't run into this problem. So, the classic birthday problem. Enjoy it, and you might be able to impress some people with this kind of probability. I don't think most people expect it to be that good. So have fun, and we'll catch you later.